Hello, I welcome you all to your own channel MSK Learnium. Now we are going to discuss about the sign convention for SFD and BMD. So for that we can take one beam that, let's say this is the simply supported beam. So whenever the load is act on the beam is subjected to the bended, right? So the load is act, so because of this load the beam will be bended in this manner. Is it or not? This is the shape we'll get. It means that if I draw it here, that the bended portion of the beam, if I draw like this, so the bended portion of the beam will look like this. Is it or not? It means if you have taken one section, this is the, let's say this section is XX, right? So this is the x-axis, this is your left hand section, and this is the right side section. So if you see that because of this load and as the beam is bended, so if the rotation from the left hand side, it will be clockwise, okay, and from the right hand side if the rotation is anti-clockwise, so that moment will be the positive bending moment. Means if the beam is bended and the rotation from the left hand side towards clockwise and from the right hand side towards anti-clockwise, it moment will be positive. Or again you can say that as the beam has bended and the concavity at the top, so this is your concave, right? So this is the concave shape you got. So if the concavity at the top, the moment will be positive bending moment. Now the positive bending moment is also known as the sagging moment. So you can write here, if beam bended in such a way that concavity at the top, okay, so the bending moment is positive, right? We'll get the positive bending moment. Or you can say the positive bending moment is known as sagging moment, okay, is known as the sagging moment, right? Again, that from the left hand side if it is the clockwise, and from the right hand side if it is the counterclockwise, the bending moment will be the positive. Next we can say, or another way you can say, whenever the beam is smiling, so you can see this, the smiling face of the beam, right? So whenever the beam is smiling, it means that the moment will be the positive. Next case is that, suppose you have one beam is like this. Let's say this is the cantilever beam, so this is fixed here and the load is acting here, right? So maybe the load can act here also. So when the beam is loaded, then the beam is bended in this fashion. Is it or not? This is the bending will takes place. So when you draw this shape of the bended portion of the beam, so the beam is bended in this manner, right? So it means you can see here, you can observe that in this case the convexivity at the top, or if I take one section, this is the x and this is also x, right? So this is your left section, and the left section the rotation is takes place counterclockwise, right? And from the right section the rotation is takes place clockwise. So whenever the beam is bended and the rotation from the left hand side is anti-clockwise and from the left hand side clockwise, the moment will call it as a negative bending moment, right? And the if or else you can say that if the convexivity at the top, it will be the negative bending moment. So further you can make a point, if a beam is bent in such a way that convexivity at the top, right, is a negative bending moment, right? Is a negative bending moment. And another point you can make, that negative bending moment is known as hogging moment, right? Is known as the hogging moment. right? So two way you can say, whenever the beam is bended, the left portion is rotation is clockwise and the right side the rotation in anti-clockwise, it will be positive bending moment. Positive bending moment is a sagging moment. Next is what, that if the beam is bended in such a way that from the left hand side it is anti-clockwise and from the right hand side clockwise, it is negative bending moment, or negative bending moment is also known as the hogging moment, right? So or in if the beam is bended and the concavity at the top, it will be positive, okay, concavity at the top, and if the convexivity at the top, it will be negative. Next we will see the bending shear force, means sign convention for the shear force diagram. So next you have a sign convention for shear force. That is, for shear force you can see, that is shear force. So let's say one beam we have taken, okay, so on the beam, let's say this is one section we have considered, that is XX, this is your left and this is your right. On left or right, the load can act in a two way. Either the load can act vertically up or the load can act vertically down. Similarly, on the right hand side also, the load can act up or load can act down. Okay, so if you have a you do the calculation from the left hand side, right? So if you are calculating the shear force from the left hand side and you find that the left hand side the load is acting vertically upward, right? So left side upward is positive, that is LUP, left side upward is positive, right? Similarly, you have a, if you are starting from the right hand side, right, and the right hand side downward forces, so RDP is positive, right side downward is positive, right? Now similarly, if you are starting calculation, means if you are finding the shear force from the left hand side, so from the left hand side downward is negative, that you call it as a LDN, left side downward is negative. If you the forces is means your calculation is from the right hand side and it is upward, so RUN, that is right side upward is negative. So if the beam is given and you are doing the calculation from the left hand side, and left hand side upward the shear force will be positive, left side downward is negative, right side upward is negative, and right side downward is positive. So this is what you have a sign convention for shear force diagram. Now we will solve one numerical problem and then we'll see how to draw the SFD and BMD. First of all, we have started the shear, means today we'll go the we'll discuss the problem of a simply supported beam, and that beam is subjected to the UDL as well as the point load. That means you can say that it is the combination of UDL and point load. So let's start. So the problem is on the screen. You can see a simply supported beam of length 10 meter carries the uniformly distributed load. A simply supported beam of length 10 meter carries the uniformly distributed load and 2 point load as shown in the figure. So figure is here. Draw the SF shear force and bending moment diagram for the beam. Also calculate the maximum bending moment. So you have a simply supported beam is given of having length is 10 meter, right? So A, B is the beam, and at the point 2 points load acting 50 kilonewton and 40 kilonewton, as well as one UDL is acting of having magnitude is 10 kilonewton per meter. So the point load, first point load is 50 kilonewton at a distance of 2 meter from the A, and the next is at a distance of 6 meter from the A, and up to 4 meter length the UDL is acting whose magnitude is 10 kilonewton per meter. So this is the problem of simply supported beam. So whenever the simply supported beam problem is given, you need to find out the reaction, right? So that is RA and RB we have to find. So let's do that. Here you can see, this is your reaction at A is RA and the reaction at B is nothing but the RB. Simply you can use the equilibrium condition, that is this RA plus RB is RA and RB is acting upward, and 50 kilonewton, 40 kilonewton and 10 kilonewton UDL is acting downward, right? So these forces, sum of these forces should be equal to the sum of these reaction. So you can say here that RA plus RB is equal to what? 50 plus 40, 10, 90, and this UDL is given. So you know that whenever the UDL is given, that UDL should convert it into point load. How to convert this UDL into point load? You can look at this. UDL is acting up to 4 meter length, right? So when the UDL is given, you just multiply the given UDL with the length over which the UDL is acting. So the UDL 10 kilonewton per meter UDL is acting up to a length of 4 meter. So when you multiply this UDL with this length, it becomes point load, right? So now you can say 50 plus 40 plus 10 into 4. Why 10 into 4? This UDL should convert it into point load. How? By multiplying with the length over which the UDL is acting, right? So now you can say the RA plus RB is equal to 130. Let us say this is equation 1, right? So now we can take the moment about any point. So let's say they take the moment about A. So I am writing here, that is taking moment about A, right? So when you take the moment about A means what? Let's see this. This force RB is acting vertically up. So as you know that moment concept, so when the force is acting, RB is this way, it will be rotated in the anti-clockwise direction, is it or not? Anti-clockwise. And because of this 50 kilonewton, 40 kilonewton and this UDL is acting downward, so about this point the moment will be clockwise because of these three forces, right? And but because of this vertical reaction, the moment will be anti-clockwise. So anti-clockwise will be one side and clockwise will be another side. So now you can say this total length is what? RB into 10, that RB into 10 is equal to this 50 is acting what distance? 2 meter. Force is perpendicular and distance is horizontal. So 50 into 2. Again 40 into this total. 4 plus 2, 6. But this UDL. So first this UDL should convert it into point load. So where this point load will act? That point load will act into at the center of gravity, right? So for this center of gravity of this length, means for what length? For 4 meter will be the half of the 4. But you are finding the moment about this point. So this length should be added. So let's see that. So you can say 50 into 2 plus 40 into 6 plus these two are point load, right? Now this 10, that is UDL, as I multiply this 10 into 4, it becomes point load. Why? Because this UDL is acting up to a 4 meter length, right? So now it becomes point load. Where this point load should act? This point load will act at the center of gravity. Center of gravity of the length is nothing but the half of the span. That half of the span is what? 4 by 2. But you are finding the moment about A. So as you have taken 4 by 2, it means that just you get the values from here to here. Just see my pen, right? From here to here you get the length. But this more length, this length should be added. Then only you can get the moment about this point. Okay. So this length is what? 2. So it means that 4 by 2 plus 2. Don't be confused. Right. So now, so this is 10 RB is equal to 500. Right. So RB is equal to what? RB is equal to 50 kilonewton. So one of the reaction we got, substitute this value into this equation, you will get the RA, right? So RA is equal to what? That RA is equal to 80 kilonewton. Okay, now these two reaction we got. Now we will start calculation for the shear force diagram, that is SFD. Okay, so for finding the shear force, it is up to your wish. Either you can start calculation from the left or from the right. There is no restriction in case of simply supported beam. But if it is the cantilever beam, that you should means you need to do the calculation always from the free end, right? Not from the fixed end. But it is simply supported, so it is no restriction at all. Means you can start either from the left or from the right. So now I am starting from the left end, right? So here you can say shear force diagram, SFD, right? So first of all you can say shear force at A, shear force at A, right? If you look at the figure, that shear force at A we have to calculate, is it or not? Okay, shear force at A we have to calculate. At A, this is your left hand side, you are calculating from the left, so left side upward is what? Positive LUP, so this is positive, right? So shear force at A, FA, that is symbol for shear force, FA is equal to plus RA. Why? Because it is left side and upward, so positive. So that is equal to FA, shear force at A is nothing but the 80 kilonewton, right? That is plus 80 kilonewton. Again, if I show you, so this you can see between, sorry, this is C and this is the D, right? So between A to C we don't have any other forces, right? It means that the shear force remains constant between A to C and the value is 80 kilonewton, right? So you can write here that shear force remains constant between A to C, and that is equal to plus 80 kilonewton, right? Now, but when it reaches to the C, there is a point load as well as the UDL is also, means that two way you have to find out the shear force at C, that is just RHS of C, okay, and just RHS of C. RHS of C means what? That C this. So if you see here, this is the C is there, right? So now till here means before C you have a shear force is 80 kilonewton, but when you come to this point, means when you leave this C, you got the 50 kilonewton load is act, means this 50 kilonewton will give you the impact on the beam, right? So now you can say shear force just RHS of C, right hand side of C. Right hand side of C means what? The right hand side of C means that only just RHS, means I told you, means only will use the point load. RHS of C is what? That is 50 kilonewton of load is acting, which is vertically downward, it is left side, so it will be negative, means this we can say is equal to 80 minus 50. This is what? 30 kilonewton, right? Now we can find out the that, and then after C till D you have a UDL, right? So now you need to find out the shear force just LHS of D. LHS means what? That means you are including the UDL but not point load. For point load you can say the RHS of D, okay? Now, so just wait. So now you can say here that shear force just LHS of D, right? LHS of D. So shear force LHS of D is what? Till RHS of C we have a 30, so you can say, or it's better, RA minus 50, right? This RA minus 50 and minus this 10 into 4, right? So you can see here minus 10 into 4 is what? RA is 80 minus 50 minus 40 means 90, and this is the minus 10 kilonewton. So now you can see that just before D the shear force has changed its sign from positive to negative, okay? It means that between C to D we have to locate one point where the shear force is becoming 0. That we will do later on. Now before that we need to find one more shear force that we have, means now we need to take that point load at D, right? This because of this also. So now you can say the shear force just RHS of D, right? So now you can say the shear force just RHS of D, right? So RHS of D means what? It will be RA minus 50 minus 10 into 4, that UDL is converted into point load, minus 40 kilonewton, right? So this will be your 80 minus 50 minus 40 minus 40, 130, and this will be your minus 50 kilonewton, right? So this shear force just RHS of D we have a 50 kilonewton. Now we need to see that the shear force between D to B. There is no load is acting between D to B, it means it is remain constant, and that constant value is 50 kilonewton. And if you see the reaction at B, we already calculated the 50, it means the calculation is correct. So now you can say finally that shear force remains constant between D to B. Okay, and that is equal to what? Which is equal to minus 50 kilo Newton. All right. Now, so now we need to find out that as I told you that between C to D, shear force changes its sign from negative to positive to negative. It means between C to D there is one point where the shear force is become 0. That point we have to find first. So now you can wait. So now you can say that we are considered see actually at 50 here just what is called just RHS of C we got the values as a positive, right, and at just LHS of D we got negative. It means between C to D there is a point where the shear force changes its sign from positive to negative, means the shear force is 0, right. So that point we need to consider when we have to find, locate. So now we can say, just wait, it's little bit now. So now we can say the consider any section XX at a distance of X, right, from A. So for better understanding, I'll draw this. The given beam is again, this is your simply supported beam which is given in the question, right, and here you have a UDL is acting. This is 50, this is 40, this is 2, this is 4, and this is also 4, right. So A, B, C and D. This is 50, this is 40, this is 10 kilonewton per meter, right. Now, so what I told you that shear force we have to consider means 0 between C to D, right. So now we are considering, consider any section XX at a distance of X from A. So from A I am considering, let's say this is the section X, and okay, and this distance is what? The distance between A to XX is X. So here we are considering that the shear force is becoming 0, but what is the value, means at what length the shear force is become 0. So that length, whatever the values of X, that is the length of the point, position of that, right. So now for that means at this section we have to find out the shear force. So for that you can say Fxx is equal to what? Ra, this force vertically upward left side, minus 50, right, that is vertically downward on the left side, and this UDL 10, but this distance is what? This distance we have to calculate. So the total is X and this is 2, right. So this is X minus 2, minus 10 into X minus 2. This is the shear force value or shear force equation we got at a XX position, right. So you can say that shear force at XX is nothing but the 8 is 80 minus 50 minus 10 into X minus 2, right. So this is what? 30 minus 10 into X minus 2, right. Okay, so then that we are considering the shear forces become 0 at XX. So this we can say Fxx is equal to 0, which leads 30 minus 10 into X minus 2 is equal to what? 0. So this 30 will come to this side, right. So and 10, that is minus 10 is equal into X minus 2 is equal to minus 30, minus minus will get cancelled, 10 is 3, so x is equal to 5 meter, right? On calculation we got the 5 meter. Means you can say the shear force has become 0 at a distance of 5 meter from A, right? So now whatever the x you have considered, this x is nothing but the 5, right? So here you also know that dm by dx is equal to F, right? That while we derive the relation between shear force, load, shear force and bending moment, there we'll see the dm by dx is equal to F. Means what? Wherever the shear force is 0, at that point the moment will be maximum. So while you finding the bending moment diagram, you have to find out the maximum bending moment at a distance of 5 meter, right? So this is what position we located. Now we'll go to the bending moment diagram. Okay, so let's do fast. That is BMD, bending moment diagram. Always you remember that bending moment at the end in simply supported beam is 0. So we can say the bending moment at A. Okay, so this is what MA is equal to 0, as well as I can write bending moment at B, right? MB is equal to 0. Why? Because at the end bending moment will be 0. Now we find out the bending moment at C, D and one point where the moment is or shear force is 0. Okay, so now here you can say now that bending moment at C, right? So MC is equal to what, right? So for that we can see the figure, that this is your figure, right? C is this one, MC is equal to what? RA into this. And if you look at this, that this is the point, right? So when the beam is bended, so beam is bended how? Rotation is how? The rotation is from the left hand side, it will be the clockwise. When the rotation is from the left hand side clockwise, it is the positive bending moment, right? So or sagging moment we are getting, means, or you can say the concavity at the top. So many way you can explain. So bending moment at C is what? RA into distance, that 2. So RA is what? 80 into 2. It is plus 160 kilonewton meter, right? Now then again you can find out the bending moment at D, right? Bending moment at D, right? That is MD is equal to what? See this very carefully right now. So this is your D. Either you can do the calculation from this side or from this side. So this side it is very easy. If you want to know from this side, so it is what? RA into 6 minus 50 into 4 minus 10 into 4 into 4 by 2. But if you come from this side, it will be simply RB into 4. So we'll do this from the RB into 4 only. And this is how, this is your right side, and from the right side it is the anti-clockwise rotation. So when anti-clockwise rotation from the right hand side, it will be the positive bending moment, right? So bending moment at D is nothing but the RB into 4. And what is the RB you have? That RB you got 50, right? So it is 50 into 4, which is plus 200 kilonewton meter, right? Now we need to find out the maximum bending moment. So for that, as I told you, this is the section. At this section XX, again you have to find out the moment. So moment is what? Force into distance, that is RA into X. This is positive, and 50. Why? Because this is your left side, and because of this load, the rotation will be anti-clockwise, right? So from the left side, anti-clockwise is negative. 50 into this distance is what? This distance is X minus 2, right? Again one more load is UDL is acting, which is 10. So this first UDL is converted into point load. How? 10 into X minus 2, and this point load will act at the center of gravity, that is X minus 2 by 2. Okay, now you can say the MXX, that is bending moment at a position XX, is what? RA into X minus 50 into X minus 2 minus 10 into x minus 2, this is 10 into x minus 2, as I multiplied it become point load. Where this point load should act? It will act at the center of gravity, means x minus 2 by 2, right? So if I simplify this, that is RA is what? 80x minus 50 into x minus 2, this 2 to 5, so minus 5 into x minus 2 whole square. Alright, so this is, we got the moment at x6, right? So where that means maximum bending moment we have to find out. So for finding the maximum bending moment, we need to see where the shear forces become 0. So as we have calculated, the shear forces become 0 at a distance of 5 meter from the A, right? So for here you can say maximum bending moment is at a distance of 5 meter, right, from E, right? Now, so now you can say here, just give me this second. Right, so now you can say that maximum bending moment is what? That is 80 into 5 minus 50 into 5 minus 2 minus 5 into 5 minus 2 whole square, right? So while you calculate, you will get the maximum bending moment value. M max is equal to 205 kilonewton meter, right? Now, so we got all the at each point shear force as well as bending moment. Also we got the maximum bending. Now we need to draw the SFD and BMD diagram based on this data, right? So for SFD and BMD diagram, again we have to draw the given question, which is right. So now here you have a, this is the problem is figure is given in the question, right? So let's say this is your beam, okay? So this is the A, the reaction at A is RA, and this is the B, the reaction at B is this is the, so this is the 50 kilonewton of point load is acting, and the UDL is acting up to a length of 4 meter, and again you have a 40 kilonewton, this is 50, this is 10 kilonewton per meter, this is kilonewton, and this is the kilonewton, right? So this is RA we got 80 and RB is 50, that we have calculated. So this is your 2 meter, this is the 4 meter, and this is also 4 meter, right? So the name of the beam is A, B, and the point load is acting at a C and at D, right? So now we have to draw the SFD and BMD. So for that we'll draw the line, this line we have to draw, okay? And from here also we will draw the line. So first of all I'll show you the SFD diagram. So this horizontal line will draw, and from this point we need to draw the broken line, right? So now we can say the shear force at A. So shear force at A is what? Plus 80. So let's say this is here, you can take any values, and it is remain constant between A to C, right? Now the shear force is just at C, it become how much? It become the 30 kilonewton, right? So this is what you have a 30. From this to this it is 30, right? Means 50 you have subtracted. So now again you can see at a distance of 5 meter, this total is 6. So 5 meter, at a distance of 5 meter, the shear forces become 0. That is x is equal to 5 meter, right? So it means that here you have a shear force is 0 and the bending moment will be maximum. And then how it is deviating? It is like this, it's become 0. Again if you can see shear force just LHS of D, just LHS of D is what? That is minus 10, right? So it is the minus 10 right now. And then and then at just RHS of D it will be 40. So this is 50, right? And this will be remain constant like this, right? So this is what you have a 80. This is your 10. Let me check. 30, I think. Yes, that is 30. This is 30, right? And this is the 10 minus 10, right? And again at D it will be minus 40, right? And this is minus 40 and this will be 50, right? This is the minus. So this is negative and this is the positive shear force diagram. So this is your A, B and C, D, and let's say this is the E, that at E the shear force is become 0. Now we need to find out the bending moment diagram. So for bending moment, all the bending moment we got as positive itself. So bending moment at A is 0 and at B is also 0. If you look at the bending moment between bending moment between A to C is a straight line, means we have a distance is power 1, so it will be a straight line, right? So here it is how much? First you have a bending moment at C is 160, right? So at C this is 160 and this is your D. So at D it is the 200, right? And at E it is the 205. So this is your E, right? So at E it is the 205. So how it is? This is 160 and this portion we got the, actually it is the inverted parabola. Why? Because the distance power 2, right? So this is like this is like this, and again this will be the straight line. So this is how you can draw the positive bending moment. This is 160, 205 and this is the 200, right? So A, B, C, D and E. Okay, so this is what we have a SFD and BMD for the given problems, right? In next class we will solve the cantilever beam with combination of point load as well as the UDL. So please like, subscribe, comment and share this channel. Thank you.